So we can do this as long as the output of the divider is not required in the same clock cycle both times. But the reason we do this to reduce area is because division is such a large hardware unit, so we can reduce area. But while that might be obvious for division, it's not necessarily obvious for other operators. And so really what motivates this work is that in fact different resource sharing trade-offs exist depending on which operator is being shared. So let me give an example to explain why that might be the case. Consider a 4-bit adder. So once again, consider a C program which performs addition twice now. We'll say each is a 4-bit addition for simplicity. But once again, there are two implementations in hardware. You can have separate hardware additions, like this. We'll call this method 1. Or you can have the same adder which is shared by adding multiplexing on the inputs. And in fact, which implementation is preferred depends on the architecture. So let's see how these two hardware cases are mapped to LUTs. So this is an image shown from Altera's technology map viewer. This is a single 4-bit adder mapped to LUTs in Cyclone 2. And what we notice is that there's a ripple carry implementation. So what happens is these are each just full adders. We have a 2 LUT at the beginning, followed by 2 or 3 LUTs depending on if the logic element is in arithmetic mode. But overall, we have 4 LUTs, which Quartus maps to 4 logic elements in Cyclone 2, or 2 adaptive logic modules in Stratix IV. That's for a single 4-bit adder. If we have 2 4-bit adders, which was method 1, we have 8 logic elements in Cyclone 2, or 4 adaptive logic modules in Stratix IV. So just recall that's method 1 on the left. Okay, so let's compare this now to method 2. So if we share the adder again in Cyclone 2. So now what happens is we notice that there are 8 new LUTs. They're all 3 LUTs, and they're here on the left. These are each 2-to-1 muxes, which precede the same 4 LUTs as before, which implement the ripple carry adder. So what we have is we have the same 4 LUTs implementing the addition as before, but now they're preceded by 8 new 3 LUTs, which each implement a 2-to-1 mux. And we have 8 muxes because there's 2 4-bit inputs. So overall what happens is in Cyclone 2, this is 12 logic elements. And if we compare this to before when we just had 8, we notice that for Cyclone 2, we actually prefer to not share the adder because we had fewer LUTs. Okay, so that's Cyclone 2. Let's compare this to Stratix 4 now. What we notice in Stratix 4 is that we don't have separate LUTs for each of the multiplexers. We still have 8 new muxes, but they're not each in their own LUT. We do have 2 3 LUTs that each implement a 2-to-1 mux. But we also have 2 4 LUTs now, which implement a mux and a full adder. So recall that each Stratix 4 adaptive logic module contains 2 full adders. So what happens is we see here that a multiplexer is combined into the same LUT as the addition. And this gives us 2 4 LUTs. And we also have 2 5 LUTs, which implement 2 muxes as well as a full adder. So what's happening here is that the multiplexers and the additions are being combined into the same LUT. And what ends up happening is we get 2 3 LUTs, 2 4 LUTs, and 2 5 LUTs, which Quartus does because this then allows us to pack this into just 3 ALMs. One adaptive logic module has 2 4 LUTs, and the other 2 each have a 3 LUT and a 5 LUT. And the reason this is preferred now is because rather than 4, which we had before, we now have 3 adaptive logic modules. So we see that in this case, sharing is preferred. Okay, so this was just a quick example. But what I'm trying to show is that even for something small like a 4-bit adder, there is an architectural dependence. So repeating this analysis now, not for 4-bit operators, but for larger operators of 32 bits. We do this not for just addition, but division, multiplication, as well as bitwise operations. And our goal now is to see on each architecture when it's beneficial to share each operator for 32 bits. And what we conclude is that in Cyclone 2, it's beneficial to share larger operators like division, modulus, multipliers, as well as barrel shifters. But perhaps surprisingly, in Stratix 4, there's also a benefit to sharing addition, subtraction, as well as bitwise operations. So this is our first main result. And one general conclusion we can make from these single operator results is that you get the largest area reduction when considering larger operators, so division, remainder, etc. So the next step now is, okay, so we get our largest area reduction from larger operators. So our next step now is to see if we can combine many smaller operators which occur in a C program into larger operators. So what we're doing now is finding frequently occurring patterns of smaller operators, treating these as single larger hardware units and sharing them. So in other words, creating a single functional unit that's made up of many smaller ones. So maybe this animation will clarify, but rather than share each operator individually, we can save multiplexers and save area if we share patterns of smaller operators as single larger hardware units. So that's really what we're after in this work. The single operators showed motivation for this, but this is where most of the area reduction will come from. Okay, so those are some of the key ideas that show this resource sharing technique. Now we'll talk about how these are implemented in LEGUP and the algorithm that's used. So LEGUP goes through a 3-step algorithm to implement this pattern sharing. The first is to find all the computational patterns which exist in a given C program. The second is then to group together equivalent patterns that can be implemented using the same hardware. And then once we have all these groups of equivalent patterns that can be implemented using the same hardware, we select pairs to be implemented using a single function here. So I'll go through each of these steps. The way that LegUp represents these computational patterns are as data flow graphs. So this is an example of a size 5 graph. Each node in these graphs represents an instruction, and there's a single root or output node, just like an operator has a single output, but it can have multiple inputs. So this is an example of a size 5 graph. So the first step in LegUp's algorithm is to find all the computational patterns that exist in a software program. LegUp has access to a data flow graph which represents a compiled C program. And so step one now is to take this data flow graph representing the entire C program and to find subgraphs within this graph, or computational patterns which exist. So I'll show an animation to clarify this. So let's say that LegUp's data flow graph representing a compiled C program is this graph. Each node here represents an instruction. I haven't shown what they are, but each node here is an instruction. Let's say that some of these nodes aren't instructions that we want to share, for example, a branch instruction. And then given the remaining nodes now, what we do is we want to find all the subgraphs of these remaining nodes. So I'll explain this algorithm. So what we do is we traverse each of the remaining nodes, which haven't been canceled out. We traverse each one by one. When we get to a node, we fix that as the root node, R, and then perform a breadth first search of all the predecessors of that root R to find all the subgraphs rooted at that node. So let me show you what I mean. So we fixed a single root node R, and then we perform a breadth first search. That's a size 2 graph rooted at R. That's a size 3 graph rooted at R, another size 3 graph rooted at R, a size 4 graph, etc. Those are all the predecessors, so we stop. We've exhausted all of the predecessors of that particular root, so we move on to the next root, repeat the breadth first search. Okay, so in this way we can enumerate or discover all of the subgraphs within this graph, so all of the computational patterns. That's step one. At each step, once we discover every graph, what we do now is we insert them into a container, which sorts them by isomorphic equivalence. So what that means is that two graphs might not be topologically the same, but we can in fact still represent them or implement them using the same hardware. So for example, these two graphs are isomorphically equivalent, which means there's a one-to-one mapping of nodes from one to the other. But because addition is commutative, you can switch the operators. So these are not topologically equivalent, but you can still implement them using the same hardware, which is what we're after. That's step two. And then steps 1 and 2 now have provided us sets of equivalent graphs. So sets of graphs which can be implemented using the same hardware. So for example, if we're considering this pattern, which is a size 2 pattern, a subtraction feeding into an addition, we might have 4 instances of this in our C program. I've called them A through D. And so now what we're after is to take 2 of them at a time and implement them using the same hardware. So the problem we're trying to solve now is given multiple instances of the same pattern, to select a pairing of these and implement them using the same hardware. But that's a difficult problem to solve. What's the best way to choose the pairing of each of these, to choose pairs of these sets of graphs? So to do this, we define a cost function which considers the bit widths of the operators. So let's consider a small example. Let's say we have 3 additions, 3 adders, each are 32 bits. But let's say that for adder C, it feeds directly into a bitwise AND by a constant binary 6 bits, so 63 constant in binary. What this does is it masks the first 6 bits of the addition. And so most synthesis tools then will recognize this and optimize this to just a 6-bit adder. So now let's say that we wanted to share 2 of these and we pick B and C. That's actually a bad idea because C is a 6-bit addition, and if we share it with B, which is a 32-bit addition, we're forcing a 6-bit addition to be implemented using a 32-bit adder, which is wasteful. So alternatively, what we should do is share A and B and then allow C just to be synthesized by most tools. So with that as motivation now, what we do is we define a cost function for sharing 2 patterns. So that should be a bit higher. But we define a cost function for sharing 2 patterns as the absolute value of the difference of the bit widths of each of their corresponding nodes. So recall that in order for 2 patterns to be implemented using the same hardware, they have to have a one-to-one correspondence of nodes. That means they're isomorphic. So what we do is we visit each of these one-to-one correspondences of nodes and we add the difference of the bit widths. So the idea here is that a smaller cost is better because it means that the bit widths are more closely aligned. So that's our cost function for sharing 2 graphs. We then adjust this based on certain preferential sharing conditions. I'll give an example on the next slide. And then finally, given this cost function now, we use a greedy algorithm which, given a graph, picks its potential sharing candidate with the lowest cost. And in this way, we do this iteratively and pair up all the graphs. And once we have these pairs, then we implement them using the same hardware. So I mentioned that there are certain preferential sharing conditions which we use to adjust our cost function. So in fact, there is one of these which I'll talk about now, which allows you to save registers. So let's say that we have these two graphs. What I've shown here, the horizontal lines represent registers and the numbers represent clock cycles. So LEGO creates a finite state machine, and so what I'm showing here is that for a certain graph, the specific clock cycles where its variables are live. Now what I'm trying to show, and I'll talk about this in a bit more depth, but what I'm showing here is that if you have two graphs whose variables have non-overlapping lifetimes, and you share those patterns, then you can save registers. So let's consider case A on the left here. We have two graphs, and we see that both their outputs are required in the final cycle 6. So let's say these are each 32-bit patterns. You require 64 registers to store both of their outputs. If you were to share them, you still need 64 registers to store their outputs because both outputs are required in this final state here. But let's consider case B now. If you don't share them, you still need 64 registers in total to store both outputs. But if you share them, you can actually store the outputs of both graphs in the same registers because their outputs are never required in the same clock cycles. So the point here is if you were to pick this pairing, you'd reduce the number of registers by half, which is actually one of the largest benefits we get from resource. Okay, so that's just in addition to the cost function. Okay, so having implemented this in our high-level synthesis tool now, I'll just go over some results. So this graph shows circuit area from 13C benchmarks that LEGO has converted to Verilog in Stratix IV. So the y-axis is adaptive logic modules, and this is for 13 benchmarks. And I've shown it for 3 successive or increasing levels of sharing. The blue bar for each benchmark represents no sharing at all. The red bar represents sharing obvious things like dividers and remainders. And then the green bar is the addition of this work, so it's our contribution, which is sharing dividers and remainders, as well as things like bitwise operations and additions, so sharing patterns. And what we notice is that between the red bar and the green bar, so what this work has contributed, the geomean improvement across all circuits is 4.9% reduction, so that's how much the area has improved. And then the total reduction between the blue bar and the green bar is 9%. So what I've shown here in the red bar is sharing dividers and remainders. I didn't share multipliers because in Stratix IV they're implemented using DSP blocks. But what some other works have done is actually implement multipliers using LUTs and then share those multipliers. So if you were to implement multipliers using LUTs instead, your area would increase. And then if you share them, you'd get very large improvement. Maybe it's not practical, that's not how people would do it, but other works have done that. So to be comparable, we did the same thing in a different graph. So implemented multipliers using LUTs, shared them, and then you get 12% total improvement. And now I'll show the same results, but for Cyclone 2. The results aren't as positive. There's 4.2% area reduction, 7% total improvement between the blue bar and the green bar, and LUT-based multipliers produce 16% improvement. Okay, so just to summarize, we've shown that, in fact, the logic element architecture does have a significant impact on this area reduction technique within binding called resource sharing. In some cases, pattern sharing has produced greater than 10% area reduction. And a future work would be to modify yet another phase of high-level synthesis called scheduling to promote the creation of certain patterns which can provide further area reduction. Okay, thank you.
Any questions?
I was just wondering about the performance. You were scheduling things that are sharing resources that weren't used in the same cycle. That's part of what you're showing. So you didn't impact the cycle count by doing that, right? But
right.
Did you impact the cycle time?
Yeah, so we don't have like Fmax or critical path results, but they did get worse. I'm not sure if I have the exact graph in my extra slides. But yeah, it certainly did decrease. But we figured that if you're going to turn on an optimization like this, it's because you have maybe an area critical application. So you wouldn't do something like this if you're as concerned with speed, but rather if you're concerned with area. So certainly there's a trade-off if you're introducing multiplexing into your critical path. Eric?
So I see a variety of some applications here speed up, and some of them, shrink, and some of them don't shrink as much. I noticed the ones that shrink a fair bit, like AES, have a lot of bit-level operations. How dependent do you think the process of finding subgraphs and grouping them is dependent on constants?
Okay, so I don't have slides for this either. Okay, so the thing with constants is, I talked about one optimization with synthesis tools can do if you have like an AND gate afterwards, right? But similarly, let's say you have a constant input into an adder, and it's like a constant 5 or something. It's very small, and that adder would also get like optimized by synthesis tools. Okay, so we found there's a trade-off. If you disqualify all operations which have constant inputs, your pattern sizes decrease. And so therefore your overall results get poorer because you don't have as many patterns to share. Alternatively, if you're sharing things with small constants, then they would get optimized if you didn't share them. So there's a trade-off. So what we found is one thing you can do is say if the bit width of the constant is beyond a certain threshold, then it's beneficial to share. But in this work, what we've done is we've disqualified things which have constant inputs. But there's different, other works have done it differently. And it's easy to change this in our tool, to try different things. Does that answer your question?
Yeah.
Alex?
Okay, so we have a question from the web. It says, how are hardware resource conflicts resolved in this work?
Hardware resource conflicts. So,
Clarify.
okay, so one interpretation of that question is if you have, let's say, 2 functional units which are required in the same cycle. So in that case, I talked very early on, I said you actually can't share a divider if it's required in the same cycle, right? So is that what you think, Lena? So let me just show you this slide again. So, for example, I talked about if you're sharing these two, you have to have separate registers for their outputs. If you didn't do that, that would be a hardware resource conflict because you'd be overwriting the output stored. Is it?
It'll be a while. Yes, that was, yes.
Okay.
I also had a question
Yeah.
myself. Do you know how this would affect compile time? It might necessarily be,
Well,
obviously, like less resources, but it might necessarily be better for compile time.
okay. Well, when we did it, it was maybe like 30 minutes per benchmark in Quartus. So I didn't really notice any difference, but I didn't measure it. So I can't say for sure, but I don't think it's significant. Marcel?
Yeah, I was wondering about, you talked a little bit about how graph patterns that you see can grow or shrink depending on kind of different benchmark. I'm curious about just in general kind of the patterns that are in common in a graph, like whether it's kind of like 2 or 3 or whether you get some that are like 9 or 10 surprisingly.
You mean like common sizes?
Yeah.
Yeah, so most common sizes are around 2, 3, or 4, but it also depends on how the C program is written. So there's one benchmark called Blowfish, which actually just has one very long loop which iterates many times, and it just does a lot of bitwise operations. And the thing is that loop gets unrolled by LEGA, and so you have these very long chains of hardware bitwise operations feeding into each other. So in that case, we limited all these patterns to size 10. That's the maximum we find, so it's computationally tractable. But if we don't do that, there was like a size 14 pattern in Blowfish. So in other words, 2, 3, and 4 maybe are most common, but it can go higher than that.
I guess along the same lines, do you find that there are patterns that you can share more than twice?
Okay. So you mean rather than just pairing them, share them in 3 or 4. Okay. So something else I mentioned earlier was that we have to pair them up. So the reason I said pair them up, let me just go there. So you might say, well, why just 2? Why not 3 or 4? So the area reduction comes because the multiplexers can combine into the same LUTs as the functional units. And that's only possible if you have smaller muxes, like 2-to-1 muxes. If you start looking at 3-to-1 muxes or 4-to-1 muxes, then there isn't as much potential for the multiplexers to combine into the same LUT as the operation, and so you don't get as much of the area reduction. So that's one thing we tried, but we found that pairing them together as opposed to grouping 3 or 4 produces the best results. Any other questions? Yes?
I have a question about the optimization for large blocks like dividers, for instance. Do you always assume that when you take a single cycle for that unit to produce its result?
So,
or do you make use of the fact that it is pipelined across a couple stages, you can feed in different results at different stages?
so LEGA pipelines is adders 16-stage pipeline? Dividers, yeah, 16. So all we require is that the outputs are not required in the exact same cycle. So for example, if there's one cycle that's different, then you can still share the adder. But the thing is, if you share them and they're required in the same output cycle, one possible improvement or future work would be to delay one divider by 1 cycle so that you can still share them. So that's what I talked about in my future work, which was you can actually modify another phase of high-level synthesis called scheduling. The scheduling phase, which is when all these operations are scheduled to provide further area reduction. So that's possible, but it's not currently done. Any other questions? Eric?
So you're talking about muxes where more than 2-to-1 stress being problematic. Now this will probably only apply to bitwise operations and not stuff like adders and carry chains. But do you look at how many bits of input are required for every bit of output of a given cluster of functions? Because if you're on the Stratix 4, you have 6 levels. So that means if you know that your this group, this subgraph, has 6 bits or less of input for 1 bit of output, you can just collapse that.
6 bits. Okay, so you're talking about like 3-to-1 muxes?
Any amount of muxing.
Okay, so what we found was even, sorry.
You can combine muxing and bitwise operation in the same lookup table.
Okay.
If you know that the number of bits will be exceeded.
Yeah, so I have some slides for that too, but one thing we showed was that even with 3-to-1 muxes, you have 2 times 3 inputs plus the select bit, so that you need at least 7 inputs. Stratix 4 can handle 7 LUTs, but we just found, I didn't, I guess, check exactly why, but if you look at larger multiplexer sizes, the area actually got worse. So I could look more into that, but my guess is because it does have 6 LUTs in Stratix 4, but you need 2 multiplexers, let's say 3-to-1 multiplexers or larger, plus select bits, and maybe that's too much. But I don't know if there's slides for that. But yeah, we looked at bitwise operations and sharing bitwise operations.
Right.
Is that okay? Or, cause
Yeah, I see 1, 2, 3, 4, then you need 2 select bits.
yeah, actually, maybe if I have a couple minutes, I can just go into this. Okay, so one thing we noticed was that the circuits that LEGO generates actually tend to have a bias towards smaller LUTs. So I'll just explain this quickly, but this is the same 13 benchmarks, but it shows the proportion of LUT sizes for the different benchmarks. The blue bar shows size 2 to 3 LUTs. So what we're showing here, just really quickly, is that for each benchmark, the majority of the LUTs are size 2 to 3. So we have a majority of smaller LUTs. So if you do something like this now, and you share a bitwise operation, which seems really unintuitive, what you can do is you can take, okay, so for each of these you need 32 LUTs. They're small LUTs, but you have to have 64 outputs. So 32 times 2 is 64 LUTs in total. That makes sense, right? Okay, if you were to share them now, you'd reduce the number of LUTs by half, but their size would grow very much. You have 2 plus 2 plus a select bit, they all become 5 LUTs.
Yeah.
Okay, so, but that's actually not a problem because even though you're increasing the LUT size at the expense of reducing the number of LUTs, because we have so many smaller LUTs in our circuits, like size 2 to 3 LUTs, and because Stratix 4 ALMs can have 3 LUTs and 5 LUTs,
Yep.
then actually this is okay because if we reduce the number of LUTs, but increase their size to 5, they can still be incorporated into the same LUTs which have a lot of 3 LUTs or 2 LUTs from before.
Oh, that's cool.
So I have these sort of as backup slides, but that's the rationale behind Stratix 4. Actually, you get improvement from sharing something like a bitwise AND, which is really unintuitive. But that's the explanation behind that. Alex?
One question. One thought about the resource sharing. Assume that the adder can run at 300 megahertz and the rest of the circuit runs at 100 megahertz. Do you think that time sharing is possible, and how hard would it be to implement?
Time sharing. What's
I guess time multiplexing.
Like in one system cycle, because adder is so fast, you could maybe do 2 additions in one system cycle. You kind of double
Oh, I
clock
see.
the
In
adder.
this case, 3, because it'd be 300 to 100 megahertz.
Okay, so LEGO currently does that with its memory. It uses something called multi-pumping memory, where it runs the memory at twice the speed. I think Eric talks about that in one talk, and James will talk about it soon. We haven't looked at that with functional units, but that's certainly a future work as well. Any other questions?